Hello, welcome to the EPG Pathshala on Linguistics. I am Dr. Reenu Punus, affiliated to the Jawaharlal Nehru University, New Delhi. I will now be taking you through the module titled Introduction to Experimental Phonetics, Part 2. In a previous module titled Introduction to Experimental Phonetics, Part 1, the field of experimental phonetics was briefly introduced and the term explained. The focus then shifted to one of the subfields of experimental phonetics, articulatory phonetics. Some of the major methods used in this subfield were described, and a case study was presented to highlight how some of the methods described in that module have been used by researchers to arrive at a better understanding of the complex processes that underlie speech production. In this module, the two other subfields of experimental phonetics, namely acoustic phonetics and auditory phonetics, will be introduced vis-à-vis the methods used in these subfields. Case studies exemplifying the use of some of these methods in research to address some important issues or questions in the field will also be described. Acoustic phonetics is the branch of phonetics that is interested in the transmission of speech in the form of sound waves from the speaker to the listener and the physical properties of these sound waves that characterize speech. Sound waves are essentially variations in air pressure caused due to the movements of the speaker's vocal cords. Acoustic analysis of speech mainly involves identifying the physical properties of the sound waves that characterize the speech. Before we review some of the analytical software that helps us to understand the various physical properties of speech, it is important to remember that the software converts the speech signal in a sound file to different kinds of visualizations. For example, waveform, spectrogram, etc. Therefore, only if the quality of the speech signal is good can software programs do their job efficiently. To ensure that a good quality speech signal is recorded, factors such as the kind of equipment used and the speech environment are very important. A large majority of research in experimental phonetics has focused on laboratory recordings or recordings made in lab-like conditions. Care is taken to ensure that background noise is minimal in order to obtain good quality audio recordings. Although there is no hard and fast rule regarding where the recordings need to be made, there is a trade-off between the naturalness of a speech setting and the quality of recordings obtained. Many studies that fall under the rubric of experimental phonetics have often been criticized for the artificial nature of the data collected. Phoneticians, on the other hand, point out that the speech environment surrounding naturalistic speech tends to be noisier and therefore does not lend itself well to acoustic analysis, which relies on neat recordings for ease of isolating speech sounds of interest and making reliable measurements. The technical specifications of the equipment used in collecting and storing recordings are another important determinant of the quality of acoustic data that will be obtained. Two of the main recording equipments in phonetic research are recorders and microphones. Instruments used to record and store audio data have advanced greatly, both in technological strengths as well as size and portability. In recent times, digital recorders have become the most widely used for the quality of recordings they produce and the formats in which they record. WAV, MP3 and other digital audio formats, and for the ease with which digital audio files can be stored on a computer for playback and analysis. Most digital recording devices now include internal microphones, but the use of these is not recommended for the purposes of collecting data for acoustic analysis. External microphones are a must for experimental phonetic work and are available in various sizes and types, from handheld microphones to lapel and head-worn microphones. Although digital electronic computers began to be successfully used in the 1950s, it was only in the 1960s that computers were first employed in speech research. Since then, advancements made in computer technology have resulted in the use of increasingly sophisticated procedures in speech research. Several computer programs are available for analyzing the speech signal for its various components. While the decision regarding which one of these would be most suitable would depend on the particular objectives of the study undertaken, some of these are more commonly used than others. We will now look at some of the software programs for acoustic analysis which are available online for free download. Praat is one of the most widely used speech analysis software and is developed by two Dutch phoneticians, Paul Boersma and David Wienik. In Dutch, Praat means talk. Praat offers extensive features which include speech analysis, spectral, formant, pitch, intensity analysis, labeling and segmentation, writing algorithms, creating high-quality graphics based on the audio samples, speech manipulation, and statistics. It is also capable of reading and writing sound and other file types. The official website, www.praat.org, has a useful help menu which includes extensive tutorials on how to use Praat's different features. WaveSurfer is another open source tool for sound analysis, visualization, and manipulation, developed at the Center for Speech Technology in Stockholm, Sweden. Both beginners and advanced users can use WaveSurfer for a diverse range of tasks in speech research. Most commonly carried out applications include sound analysis, speech transcription, and annotation. Like Praat, several sound and other file types are supported by WaveSurfer. More details can be found at www.speech.kth.se/wavesurfer. The latest version can be downloaded from sourceforge.net/projects/wavesurfer. SIL Speech Analyzer. Developed by SIL, originally called the Summer Institute of Linguistics and now referred to as SIL International, the speech analyzer can perform various tasks including spectral analysis, calculating, plotting and visualizing fundamental frequency, pitch, intensity and duration. It also allows for various levels of transcription, phonetic, phonemic, orthographic and tone to be presented alongside each other in an interlinear format. It also offers features like repeat loops and slow playback that can help the perception and imitation of sounds for language learning. Speech Analyzer can be downloaded from www.01.sil.org/computing/sa/sa_download.htm, and more information can also be found at their official website. Speech Filing System, or SFS, is developed and copyrighted by University College London and is provided free of charge to research institutions for non-profit use. It is a software tool that comprises different data and file types, graphics, programming languages, and tutorials to guide users. Some of its main features include displaying and labeling sound signals, spectrographic and formant analysis, calculating formant frequency measures and annotation, etc. More information on SFS is available on www.phone.ucl.ac.uk/resource/SFS. These are only a few of the free speech analysis software available, and this is by no means an exhaustive list. We will now look at an example of how acoustic analysis has been used in phonetics research. Chow and Chen, in their 2008 study, compared voice onset time (VOT) patterns of phonetically voiceless word initial stops in Mandarin and English as spoken by 11 Mandarin speakers and 4 British English speakers. Voice onset time is the time interval between the stop burst, or in other words, the release of the stop closure, and the onset of the following vowel. Based on seminal work first done by Lisker and Abramson in 1964 and later by Che and Ladefoged that examined VOT patterns of stops in several languages, 3 VOT categories were classified by the former researchers, namely -125 to -75 milliseconds, 0 to +25 milliseconds, and +60 to +100 milliseconds. 4 categories were classified by the latter researchers: unaspirated, with mean VOT around 30 milliseconds, slightly aspirated with mean VOT around 50 milliseconds, and aspirated with a mean VOT around 90 milliseconds, and highly aspirated with a mean VOT of +90 milliseconds. It was also established in earlier works that VOT varies with place of articulation, such that velar stops tend to have longer VOT measures than bilabial and alveolar stops. This is due to the relatively smaller size of the supraglottal cavity behind the velar constriction, therefore taking longer for the pressure to fall at the beginning of the release phase. 11 Mandarin female speakers aged between 19 to 35 years and 4 native female British English speakers with a mean age of 32 were recorded reading randomized word lists 5 times in a row. The word lists comprised disyllabic compound words with 2 sets of phonetically voiceless stops, aspirated per ter ker and unaspirated per ter ker, and each of the stops were followed by e, a and u, except for ker and ker, which did not occur with e in Mandarin. Acoustic measurements were made using the wave surfer software. Mean VOT values of the stops produced by each participant was calculated. To compare the results and calculate statistical significance, t-tests were conducted. Results showed that there were significant differences between the VOT patterns of aspirated stops in Mandarin and those in English. Mandarin aspirated stops per ter ker were found to have a higher mean VOT values than the English aspirated stops per ter ker. This is similar to the results reported in Rocher and Fay's 1991 study. On the other hand, voiceless unaspirated stops per ter ker in both languages were found to occupy the same range of values, the short lag region along the VOT continuum. Mandarin per ter ker was found to occupy higher and a wider range of values along the VOT continuum compared to English, but there was considerable overlap in the distribution of VOT values of both languages. English per ter ker has mean VOT values in the 50 to 90 millisecond range, which according to the Cho and Ladefoged classification falls in the aspirated category, while Mandarin per ter ker has mean VOT values around the 90 plus millisecond range. Velar ker has VOT greater than 90 milliseconds, while per ter have VOT values slightly below 90 millisecond, all of which fall in the highly aspirated category. Chow and Chen therefore conclude that their results agree with Cho and Ladefoged's suggestion to use 4 categories for voiceless aspirated stops. We will now move on to looking at the methods used in auditory phonetics. In the first half of this module, we looked at methods used in acoustic phonetics. And now we will proceed on to look at methods used in auditory phonetics. While articulatory phonetics is more concerned with the processes underlying the production of speech, and acoustic phonetics is interested in the processes involved in the transmission of speech, auditory phonetics is more concerned with the processes involved in how the listener or hearer understands the speech produced by the speaker. Auditory phonetics is broadly concerned with two aspects of the listening process. Firstly, the perception of the message by our auditory organs, how these messages are transformed into neural signals and sent to the brain for decoding. And secondly, the analysis and interpretation of the information in the verbal message by the brain. The details of this latter aspect of speech perception are still largely unknown. The basic experimental methods in speech perception research may be broadly classified into two types: discrimination and identification of speech. Discrimination experiments are those experiments which determine the participant's ability to differentiate between or among stimuli. Such experiments help to understand the perceptual boundaries and perceptual space of speakers and the possible influence of different participant groups and/or differences in the length of exposure or learning of sounds being discriminated. There are different kinds of discrimination tests used in perception research depending on the research objectives of the study. In this module, we will look at three types of discrimination tests: same different, matching to sample, and oddball experiments. For a more comprehensive view of the different types of discrimination tests available, have a look at the references section at the end of this module. The same different experiment is a common experiment in speech perception research in which two stimuli are presented to listeners in each session, separated by a specified amount of time referred to as interstimulus interval or ISI. The two stimuli may be similar or different. Four types of pairs are possible: AA, BB, AB, or BA. The listeners are asked to assess if the two sound or speech items in the pairs are either identical or different in some way. In such a design, the most common measures made are percentage of correct responses to denote accuracy and reaction time. In a matching to sample experiment, three stimuli are presented in a series such that a listener compares if the stimulus A or B is most similar to or identical to the stimulus X. In other words, the listener is required to match the stimulus X to either A or B. Depending on the order of the stimuli in the series, variations to this experiment are possible. In other words, the stimuli could be presented as AXB, XAB, ABX. The oddball experiment is more common in experiments of infant speech perception. It involves the child hearing a series of similar sound sequences and responding in some manner when he or she perceives an occasional change in the otherwise repetitive stimulus. The adult version of this task is essentially a yes or no task, meant to measure whether a change is detected by the participant or not, and involves the participant pressing a button when he or she hears a change. We will now look at identification experiments, which is the second basic type of experimental method that is used in speech perception research. There are different kinds of identification tests used in perception research depending on the research objectives of the study. In this module, we will look at three types of identification tests: yes or no, labeling, and oddity experiments. For a more comprehensive view of the different type of tests, have a look at the references section at the end of this module. The yes or no experiment is a simple task in its most elementary form, which involves presenting a stimulus and asking respondents whether it was X or Y, or whether the stimulus was present or not. The scope of this task is not limited to only the above mentioned designs. Variations of this could include, for example, a design where the choice is between X, not X, and Y, and not Y, which leads to a different result from having to choose only between X or Y. The labeling task is generally used to assess categorical knowledge, and the stimuli presented to participants tend to be ambiguous or continuous. The results provide insights into how participants group the ambiguous or continuous stimuli into various categories. In the Auditory experiment, participants are presented with multiple stimuli, often 3 or 4 stimuli in each trial, and are required to choose the odd or unique one amongst these. Many speech perception experiments also utilize multiple designs in the same study to obtain different kinds of perceptual data and/or to test different objectives. We will now look at an example of how such tests have been employed in speech perception research. A seminal paper by Abramson and Lisker in 1970 examined whether listeners' ability to discriminate between 2 or more phonemes is strengthened at the phoneme boundaries or margins, and whether the discriminability of sounds is influenced by specific language experience or reflects general phonetic categories. Voice onset time, or VOT, of stop consonants was the linguistic variable examined, as many languages have been reported to use VOT in similar ways to distinguish among stops. Phoneme boundaries were determined based on an earlier identification experiment conducted by the same authors with the same participants. Stimuli were synthetic and included 31 syllables consisting of labial stops plus a vowel of the type R. VOT was varied in 10 millisecond steps from 150 milliseconds before the burst, that is minus 150 milliseconds, to 150 milliseconds after the burst, that is denoted by a plus 150. These variants were presented to the listeners for discrimination in sets of 3, also called triads. In each set, 2 stimuli were identical and 1 was different. The task for the listener was to decide whether the different stimuli was in the first, second, or third position. The triads were prepared by pairing stimuli at 2, 3, and 4 step intervals along the VOT continuum, and thus comparing VOT differences that were 20, 30, or 40 millisecond intervals apart. Each comparison was arranged in 6 permutations, AAB, ABA, BAA, etc., for a total of 504 triads, which were split into 12 tapes of 42 triads each. Native speakers of Latin American Spanish, American English, and Thai heard the tapes over a period of 3 months. Abramson and Lisker found that their results for the Spanish listeners neither confirmed nor denied the hypothesis that discrimination is strengthened in the phoneme boundary region. They attribute the unclear result to the listeners not being well prepared for the task. For the English and Thai data, the results were clear. In the combined data and in the individual graphs, peaks of discrimination correspond to the phoneme boundaries established by earlier identification tests conducted by the authors with the same participants. Also, discrimination at the phoneme boundaries was acute at all 3 levels of difficulty, that is, at the 2-step, 3-step, and 4-step intervals. A link to the original paper by Abramson and Lisker is provided in the reference section of this module. Language-specific patterns were also found. While English has only 2 phonemes along the VOT dimension, voiced unaspirated b and voiced unaspirated b and voiceless unaspirated p. Thigh has 3 VOT categories for labial stops: voiced unaspirated b, voiceless unaspirated p, voiceless aspirated p. Accordingly, there is a large peak at boundary between the 2 English phonemes and 2 large peaks separating the 3 Thai phonemes. To summarize then, in this module, we focus on the methods used in acoustic phonetics and auditory phonetics. A few of the prerequisites involved in conducting acoustic analysis were highlighted, and 4 free acoustic speech analysis software programs have been listed and briefly described with their main features. The last section describes some of the experimental designs employed in speech perception research that fall under one of 2 broad experimental categories: discrimination and identification. Case studies were also described in the acoustic phonetics and auditory phonetics subsections to further your understanding of how the methods described in this module have been used to address questions regarding how speech is transmitted and perceived. We have now reached the end of the module, Introduction to Experimental Phonetics, Part 2. I hope that the concepts are clear. For further information, please visit the EPG Pathshala website. Thank you for your time.